Back to another video, guys. You're on a pick of the week specific selection for the most interesting problem, for my opinion, and that actually starting from GCSE and up to university course. Alright, so let's get started. Today we're gonna go through properties of bisectors where in a trapezium. That's quadrilateral with their two parallel lines as the basis and two lateral sides. Alright, so properties of bisectors is basically are less likely to be investigated in full. So that's why I decided to pick up two interesting problems, and here they are. Here is the first one, and here is the second one. Pause the video, try to do by your own as always, and let's have a look at my explanation. Before we're going to solve our two problems, I would like to mention what bisector is. So we do have actually two types of bisecting. Bisecting of the segment, that means we split on two equal halves, and bisecting the angle. In this case, we'll have a dialogue about bisector of the angle. So let's put typical angle, and let it be angle 2 alpha. So that's going to be 2 alpha. Bisector of this angle is by definition a line segment that splits your angle on two equal halves. All right. So what it means that right now you do have angle alpha here and angle alpha is there. So this is bisecting of the angle. So bisector is the line segment that splits your angle on two equal halves. On top of that, I would like to demonstrate another properties that's going to be useful. If you take any point on bisector line, here or no matter where, so the point will be equidistant to the arms of the angle. It's splitting on two equal halves. So that means if we mark this line segment as A and this line segment as B, and we take random point, let's say P, so by definition, the shortest route to segment A and the shortest route to segment B should be the same. So that's by definition what equidistant is. Why? Obviously because if you put 90 degrees angle here, because by definition the shortest route should be perpendicular from a given point to your line. So that means we arrange two angles, each one by 90 degrees. And that means considering those triangles, for example, this triangle and triangle which is below, we found them identical. So that means two triangles are the same. And that means why actually two angles alpha here, 90 degrees and 90 degrees, automatically the rest angle, the third angles are also respectively the same. And this side, which I marked as maybe bold yellow, is going to be the common side. So they share a common side over there. So that means because this common side, all sides becomes the same. They are not just congruent, they are really equivalent, so identical triangles. And that means those two distances are going to be the same because point P were randomly chosen, so we can state that any point on a bisector is equidistant. So that means bisector basically is equidistant from the arms of the angle it's splitting on. Alright, so I hope you understand that, and we can move to the first problem. Here is the problem 1. We have a trapezium ABCD and bisectors of angles A and B respectively intersect at point P. So right now I'm going to drop those two line segments, basically bisector of angle A and B respectively, trying to draw it precisely as much as I can. So for example like this, and here like this. So mention that they're bisectors, so that means they're splitting corresponding angles on two equal parts. and they intersect at point P. Here is the P point of intersection. So we know that AP is 4 centimeters, we have BP 3 centimeters, and we need to figure out the value of AB. So AB is going to be X side, all right? So how to understand, because we're not given any angle, we're not given just, we are given only the lenses. Obviously, we need to look for a specific triangle. So let's have a look at the triangle ABP. So what do you think? Is there any is it specific angle maybe at point P or at the vertex P? Of course, it's going to be 90 degrees. Why? So here is a little proof, small proof. Let's put, so you have angle B, and we can split on two equal angles. Let's say better and better here, and also alpha and alpha here. That's according to the statement, due to the fact that AP is bisector of angle A and BP is bisector of angle B. So, do you remember the theorem about two parallel lines? Of course, you should do and you should use. If we consider two bases of the trapezium, we can state that they are parallel. So we can denote using those arrows. All right, so maybe I just put it more proper in this way. Okay, so I denote using arrows of two bases are being parallel. So what it means that AB is going to be second line. So what it means that angle alpha together with this alpha, 2 alpha, becomes that angle. So this angle is 2 alpha, and together with 2 beta, they will arrange 180 degrees. So basically, they are alternate angles, and they're going to be the same. So right, so 2 alpha plus 2 beta will arrange 180 degrees, so they become complementary angles. According to the theorem about two parallel lines and a line AB as the second line. Okay, so that's the second line. All right, so that makes the fact that alpha and beta together will arrange 90 degrees. Coming back to a triangle, we can say that triangle is right angled. Okay, so this triangle is right angled, and that means angle P becomes 90 degrees. So that makes finding X pretty easy and pretty obvious. So it's going to be 4 squared and 3 squared in a row. 16, 9, 25, so X becomes 5 centimeters. And that's going to be the answer for this problem. I hope you understand. It was completely based on the properties of specific angles, which are alternate angles, and also we use complementary angles in this case. And specific properties, so we found out that triangle is right angled. Okay, so right angle. We can move on to the next problem. It's much more interesting and a bit more complicated. So here is the problem, the second problem. Here's the trapezium. In this case, we have a bit different bisectors of angles C and D respectively. So that means I just want to put those bisector from point C and from point D. Alright, so let's try to put them in this case. For example, that's going to be the first one, and let it be the second one. Alright, so those two bisector, that means we can arrange two angles respectively the same, because that those bisectors splitting those angles, and right now they have intersection in the point P. All right, so we need to prove that point P is equidistant from lines BC, AD, and CD. All right, so what it means equidistant? It means that if I use, let's say, arrows and put blue lines for them, blue color, so equidistant means that the side distance to side AD the same as distance to side CD. So I try to put perpendicular to CD. And also, if I prolong the line BC, maybe changing the color, so let's prolong BC in this way. Because if even it's not necessarily that you need to put perpendicular exactly to the segment BC. It can be to the extension of BC. It's going to be the same, also the distance. All right. So if you put the third distance to the line BC, all distance will be the same. So you need to prove that. If I marked them as R here, and R here, so we need to prove that they are all the same. Okay, I just eliminate them, and first of all, I'm thinking I put letters, okay, using yellow colors. Let it be K, let it be L, and let it be M. So we need to prove that PK the same as PL and also the same as PM. So we need to prove that. All right. So which property we can use? Let's have a look, for example, for simplicity, at triangle PDK, and triangle PLD, the second triangle PLD. Remember before, at the very beginning, we discussed that if PD is a bisector, it bisects the angle D, so that means two triangles should be the same. All right, so we can use this fact and we can state that this side is common, so PL equals to PK. So from there we can figure out that PL is going to be the same as PK. All right, so we've done that, and right now let's consider another two triangles, which are PLC, and another triangle PMC. Those two triangles are also the same because in this case PC is going to be a bisector of angle C. So what it means that PM is going to be the same as PL. So hence from there we can figure out that PK is also the same as PM. And that means we proved that point P, point of intersection of bisectors of angles C and D, are the same. So this point is equidistant to sides BC, to side CD, and to side AD. That's pretty obvious. And on top of that, you can even use the fact, if you put the circle, let's use yellow circle, maybe a bit bolder, because PM, PL, and PK, they're the same distances, you can put the circle with the center P and try to put in the way so that those distances becomes radius. All right, so that's pretty obvious. So that means you can inscribe partly so that and make your circle touching sides of the trapezium. All right, so AD at least and CD, and extension of the side BC. Hope you like that. Don't forget to subscribe if you're new here. Sorry for a long absence. I've been filming dance clips because right now primarily my focus on making dance videos. So I'm not sure about doing math so frequent as I did before. I try my best, and also I think I'll be doing physics as well. All right, but it depends on time. So share in comments what you like to see in the nearest future. That was Daniel Dallas. Hope you like that, and see you next time.